Then I'll talk a little bit about the basics of Bayesian inference. Then I'll talk for a little bit about a theorem called the Bernstein von Mises theorem. And essentially what the theorem says is that in most cases, in practice, it doesn't make any difference whether you do work from a Bayesian perspective or from a frequentist perspective. In some sense, that is an incredibly important result. And so it allows people to typically be somewhat vague about what they're actually doing. And partly I'll use that to argue that pretty much all empirical work is really implicitly Bayesian, and that in cases where, and that's sort of, I'll try and make that point by sort of discussing a couple of cases briefly where Bernstein von Mises doesn't apply, and where doing things from a frequentist perspective makes things very, very complicated. Then I'll talk about some of the sort of the main advances in Bayesian work in the last 15 years, which is really computational, and sort of these methods are generally referred to as Markov chain Monte Carlo methods, which allow people to use Bayesian methods, to use formal Bayesian methods in a much wider class of problems than was possible before, and to now make these Bayesian methods actually much more applicable than frequentist methods, much easier applicable than frequentist methods in a lot of cases. And then the rest of the time, I'm going to discuss 5 examples. I'm going to look at some of Rossi's work, where he looks at demand models with unobserved heterogeneity and preferences. I'm going to look at some of Chamberlain's work, looking at panel data, where instead of just allowing for individual specific intersets, he allows for both individual specific intersets as well as individual specific variances. And it turns out there's a lot of evidence for heterogeneity in variances. They can potentially make a big difference for substantive questions. I'll look sort of very briefly at some work I did with Chamberlain, looking at instrumental variables methods with many instruments. I'll talk more about that setting tomorrow, but here I'll look briefly sort of at a Bayesian perspective on that problem. The 4th example is a paper by Gawicki and some co-authors looking at binary response with endogenous regressors, kind of showing what type of models would work well there from a Bayesian perspective. Last example is a model with a discrete choice model with multiple unobserved choice characteristics, where again, from a frequentist perspective, that would be very difficult to handle. The likelihood would be very complicated and multimodal, but from a Bayesian perspective, that is conceptually very straightforward to analyze. So by way of introduction, it is surprising, especially compared to the statistics literature, where Bayesian work is probably almost about 50% of the papers in journals these days. There's actually very little formal Bayesian work in empirical work in economics. That's sort of surprising for a couple of reasons. One is that these methods are actually often very attractive from a computational perspective and from a modeling perspective, especially in settings with many parameters, sort of random coefficients settings, where large sample approximations tend not to work particularly well. So part of the reason there, at least my interpretation of that is that in a lot of these cases, but in a lot of standard cases, without too many parameters, Bayesian methods is going to be very similar to frequentist methods. And this is the Bernstein von Mises theorem, and I'll be a bit more specific about that in a bit. But so in many cases, it doesn't actually matter. And so in the few cases where it does matter, people have tended to stay away from that. But sort of also surprising because in cases where Bernstein formesis doesn't apply, frequentist methods can be extremely awkward, and sort of it's sort of very hard to imagine people doing empirical work really sticking to a formal frequentist perspective. I mean, and then just sort of to give a sort of very stylized example, but suppose you took the frequentist perspective very serious. So you wrote down a model first, you came up with a procedure for constructing a confidence interval. You weren't going to do 20 different versions of this model. You just committed to a particular model so that the p-values would really have the properties they were supposed to have. Then you got the data, and you followed your procedure. And there's some of these procedures that have been proposed that with some probability end up with empty confidence intervals. Now, how would you possibly report that? In the end, it's very hard to imagine reporting a confidence interval where you're not willing to say that at least approximately, given that confidence interval, you have 95% confidence that the parameter is in that set. But it's clear that if you have an empty confidence interval, you're completely sure by that point that the true value of the parameter is not in that set. And so the idea that you would that would be an acceptable procedure is seems. I remember a long time ago, going to some lectures by Lemer, who made this point very eloquently. Sort of called the frequentist perspective there, preposterous. It's based on these presumptions about what you would actually do given the data that clearly don't apply to what people do, and moreover, there are procedures that make no sense to actually follow. So the main case I want to make in this lecture, that in most cases, and particularly in cross-section cases of the type that we've been discussing in the lectures yesterday, sort of in these 3 days, it doesn't actually matter that you can in the end interpret confidence intervals ex post, conditional on the data is giving you 95% probability, and they make perfect sense. In cases where this equivalence between Bayesian results and classical frequentist results doesn't hold, I find it very hard to imagine sticking with the frequentist results. And so when I say that there's been very little formal Bayesian work in empirical, Bayesian papers in empirical work in economics, at the same time, there have been very few papers, certainly in using cross-section methods, where there's a serious conflict between the two. Almost all the cases that we normally look at, we get asymptotic normality, Bernstein formesis applies, and you can interpret confidence intervals from a Bayesian perspective. Nevertheless, in some cases, it can be very useful and can be a major help to be more formal about the Bayesian part and take into account some of the issues that come up, and then exploit some of the Bayesian methods. And so I'll try make a case for that. So then thinking about when I was preparing this, so in fact I talked to a bunch of people, a bunch of econometricians who were sympathetic to Bayesian methods about why they were not used more widely. And so the main reason, I think, perceived reasons were that, first of all, sort of the implications of the Bernstein formesis theorem, that in the end it doesn't matter that sort of whether you use frequentist or Bayesian methods, you get more or less the same result, and you can interpret things either way. And certainly in my own empirical work, I've done some very limited Bayesian, explicitly Bayesian work, but all the other very limited empirical work I've done that has been that was not explicitly Bayesian has all fallen into this category, where it doesn't really matter, but I'm pretty sure taking a Bayesian perspective wouldn't change the substantive results. And so the first one, I think, is a perfectly good reason. Second one is that it's that formally Bayesian methods require you to specify a prior distribution. And that's clearly a very, I think that's generally perceived as a considerable barrier to using these methods. It sort of makes these things somehow not objective. You put some information in there that you cannot directly motivate on theoretical grounds, and it may actually make a difference. So that I think that is a much less convincing reason. One reason is that in large samples, and this again goes back to the Bernstein Information Theorem, in large samples it's not going to matter unless the prior distribution is particularly dogmatic, it rules out particular values of the parameters completely, rather than being somewhat flexible. Second argument that why I don't find this particularly convincing is that in frequentist methods, we similarly rely on large sample approximations. We almost always rely on large sample normal approximations, and we pretty much ignore the issues coming from that. In a lot of cases, it's clear that large sample normality is not a particularly good approximation, but there's pretty much no alternative. We can't do exact finite sample things. Sometimes we can get slightly more accurate approximations to finite sample distributions, but those are typically very complicated and often not very satisfactory. So I think the difficulty in choosing a prior distribution is probably exaggerated in practice. Even though sort of in the statistical literature, this has led to a huge literature trying to come up with somehow a way of specifying a universal prior, an objective prior, somehow a prior that is not subjective, and that would be easy to transfer from one problem to the next. It's sort of clear that in general, a solution to that question doesn't exist. And so in the end, you cannot really avoid spending at least some time thinking about a prior distribution, unless you're in very simple cases where there's very, very few parameters where things really don't matter. Third argument that is often made is that Bayesian methods formally require you to have a fully parametric model, so that they rely on specifying a likelihood function rather than just a more limited more limited part of the model. So nowadays, so for example, generalized method of moments and all those different variations require you only to specify moment conditions. They don't require you to make a full set of distributional assumptions. And that clearly makes things more complicated for Bayesian methods. At the same time, in cases where you're interested in parameters that rely only on moment conditions, it is often not so hard to specify a relatively flexible model where the results for the parameters of interest are not all that sensitive to the specifications of the remaining part of the model. And so I'll try to illustrate it a little bit in discussing some of the examples where at the end, in all these examples, people specified fully parametric models, but I would argue that many aspects are probably not, some of the key results are probably fairly robust against changes in the specification there. And the last issue is computational difficulties, and there I think there was a very valid concern sort of up to the early 90s, but this explosion in the literature on computational methods in Bayesian analysis and these Markov chain Monte Carlo methods have pretty much taken care of that. And now, in most cases, these methods are actually much easier to apply than frequentist computational methods, to the extent that sort of for in discrete choice analysis, where for a while simulation methods, sort of direct frequentist simulation methods were fairly popular. Nowadays, Bayesian computational methods are being used there, even sort of at the expense of having to put some more Bayesian structure on that, but they tend to be much more effective than frequentist methods. So let me go to the basics. And so what I want to do is just first give it the general specification, then talk about the normal example, and so that a lot of them may be familiar from introductory statistics courses many, many years ago, but I just want to kind of establish some common language. And so part of the, so maybe it's sort of more cynical view on the lack of Bayesian work in theoretical econometrics is that in some sense there's actually very little to be done there. Pretty much the only thing you need to do is specify a parametric model, choose a prior distribution, and then the rest is all just computational issues. And there's not a lot of results to be proven, and there's not a lot of difficult theorems to state. And so in fact, it's all fairly straightforward to set up. As opposed to much of the frequentist work, where there's certainly considerably more interesting results, more challenging proofs to be done. So what is the general setup? We specify a model for a random variable given some parameters. We sort of think of that as a function of the parameter rather than the data. We call it the likelihood function. We choose a prior distribution for the parameters, so some probability function or probability mass function for a continuous parameter. Then the posterior distribution just follows from those two. Having a model and a prior distribution allows you to get the joint distribution of the parameter and the random variable. You can integrate out the parameter to get the marginal distribution for x. Take the ratio, and that gives you the posterior distribution. And so in practice, it can be very difficult to do that calculation analytically. And so one way of simplifying that a little bit is, instead of looking at the posterior distribution itself, write that without the integrating constant in the denominator, which is a function only of x, not of theta, because that's been integrated out. And so written that way, the posterior distribution is proportional to the product of the likelihood function and the prior distribution. And so that's really the key. So that's really the starting point from Bayesian analysis. We're going to specify a model that gives us the likelihood function. We're going to choose a prior distribution, and we're going to worry a fair amount about whether that's sort of a sensible prior distribution, but given that, we can infer the posterior distribution. As I said, this is kind of the key. It's not really a result. It's a result. It's sort of the key result. Years ago, when I went to Bayesian, the Bayesians used to have yearly conferences in a beach resort in Spain, and so as part of this conference, instead of giving umbrellas the way the NBER does, they would give out beach towels imprinted with Bayes' theorem. So this last result on the slide here, which was not a pretty sight on the beach, really. So now let me just go through the normal case, and so I'm going to do three versions of this, and hopefully this is all very familiar. But I just kind of want to be clear about what I'm doing here. So suppose the model, we have a scalar random variable x, which has a normal. pick the prior distribution for mu to be also be normal with mean 0 and variance 100, then what you would do and now in this simple example, you can do this all analytically. You can figure out what the conditional distribution is of mu given x, and doing these calculations, what you get is a normal distribution with mean equal to x times 100 over 101, and variance 100 over 101. That's all very straightforward. Now let's make this slightly more general. Suppose that the model is normal distribution with mean mu and still known variance, but general variance sigma squared. And let's look at what happens if we have a distribution for mu that is normal with some mean mu naught and variance tau squared. And I want to see it, see what happens for different values of tau and mu naught. In this case, you can do the same calculations. And what you get for the posterior distribution is that it's still normal with mean weighted average of the prior mean mu naught and a weighted average and the observation x with weights proportional to the inverse of the variances and with variance equal to the inverse of the sum of the precisions. And so let's kind of think about that result for a second. Suppose we're actually really sure a priori before seeing the data what the value is of mu. We could capture that by just setting tau squared equal to a very small value. That would mean that the weight given to the observation would be small relative to the weight given to mu naught, and the posterior distribution would just be very close to the prior distribution. The other extreme, if you're very unsure before looking at the data what the value of mu is, we could pick a very large value of tau, and in fact we can let tau go to infinity, and the posterior would still be very well behaved, and namely it would be normal with mean x and variance sigma squared. That's sort of a very interesting case, because now we have a prior distribution that isn't really a valid probability density function. Namely, it's flat on the whole real line. Nevertheless, it still works very well here, and we still get a well-defined posterior distribution. And it sort of would seem to capture very well the idea that before looking at the data, we're very unsure about the value of mu, and that somehow this prior distribution seems to capture it sort of seems to be very uninformative. And so this literature I was referring to earlier tried to do this in lots of cases, tried to come up with prior distributions that somehow capture the idea of ignorance prior to seeing the data. That doesn't really work in general. And in particular, it's not always a good idea to use a prior distribution that is flat. That is the way that worked very well here. But in other cases, using a flat prior distribution can actually be very informative about particular functions of the parameters. And I'll come back to that when we look at some of the examples and see some cases where using a flat prior distribution would be a very bad idea. And essentially, it's sort of the same reason why trying to estimate all the fixed effects in a panel data model can be a very bad idea. Now, last part of the normal example is the sort of same case as before, but now we have n independent draws from this distribution using the same prior distribution. We now get a posterior that is still normal, with mean still a weighted average of mu naught and x bar, and the variance given there at the bottom of the page. Now, and so I want to continue that example a little bit, but now move into the Bernstein von Mises theorem. So what happens here if n is large? So looking at, let me just go back for a second. So I want to look at the limiting distribution, at approximations to this posterior distribution if n is large. In fact, what's going to happen is that the variance is going to 0, and the mean is going to be converge to the average of the axis. And so that's not necessarily a very interesting limit to look at. So just as in frequentist analysis, it's useful to scale that up by the square root of n, by the square root of the sample size. And then if you look at the limiting distribution of the square root of n times the difference between the sample average and the parameter, conditional on the observations, so with mu still taken as the random variable, you get a normal distribution with mean 0 and variance sigma squared. And so the key thing is that limiting distribution here is irrespective of the choice of the prior distribution. In this case, it was just irrespective of the choice of mu naught and tau squared, as long as tau squared is not equal to 0. But more generally, we could have had any prior distribution as long as it had positive support on the whole real line, and as long as it wasn't too large, and we would get the same result, that the limit for this scale difference between the sample average and mu would converge to a normal distribution. Same time, sort of the most simple central limit theorem, and in fact, in this case, the exact result would be that conditional on the parameter, and so doing this by fixing mu and looking at the difference between x bar and mu scaled by the square root of n, we also get a normal distribution with mean 0 and variance sigma squared. And so what is the implication of that? If we look at a standard confidence interval, so in this case there would be x bar minus, so let's look at a 95% confidence interval, x bar minus 1.96 times the standard deviation divided by the square root of n. And so here, obviously, the way it's written doesn't make any sense. There should be a plus here and a plus there. But so that the standard confidence interval would have 95% coverage. But in addition, conditional on the data, that 95% confidence interval would have 0.95 probability of containing the true parameter. So given the data, given the upper and lower bound for the confidence interval, the probability that the parameter, you can interpret the confidence interval as saying that the probability that the parameter is in that interval is 0.95. Now, so the traditional introductory statistics books spend a lot of time arguing about the interpretation of these confidence intervals, so that it's the confidence intervals that are random, the parameter is fixed, and if you keep moving these things, 95% of the time you include the true value. Here, this is saying we can also think of it from a bit, just for a fixed interval, that the probability, given we had a particular data set, the confidence interval is 0.8 to 1.5. The probability that the parameter is between 0.8 and 1.5 is 0.95. And that's not just being sloppy, that it would be motivated by a formal Bayesian analysis where you have pretty much any prior distribution you wish. And so I'm not going to go through much detail here, but what the Bernstein von Mises theorem says is that this is true in general. Now, true in general, that sort of with some limitations, but pretty much in sort of most cases where we have asymptotic normality for maximum likelihood estimators, where we have root n consistency, so in cross-section settings where we have independent observations, we have root n consistent estimator, namely the maximum likelihood estimator. We can interpret and the statements sort of slightly more involved because so you have to rescale the parameter by the square root of n. But in the end, the interpretation is that you can interpret the standard confidence interval as a Bayesian probability interval. That with probability 0.95, the confidence interval, the true parameters in the confidence interval with probability 0.95, given the data. And this is in the end sort of, I think this is in the end the way confidence intervals are typically interpreted. It's obviously always hard to say exactly what people mean in that case, but it's very hard, I think, to argue that really what we're interested in is what would happen had we gotten different data sets rather than being interested in the coverage probability given the data we actually had. But the Bernstein-Mises theorem says it doesn't really matter. So for all intents and purposes, in a lot of the cases we're concerned with, it's fine to interpret confidence intervals that way. Now, when does this not apply? And so there's very few cases where it really doesn't apply. One of them is, and so these are not cases I typically worry about. That's sort of partly why we're not doing much time series these 3 days. But so one case where it really doesn't apply is in unit root settings. If you have a simple autoregressive model, then it's still true that if you look at the likelihood function, it's perfectly well behaved. If you have a normal prior distribution for the autoregressive parameter, you get a normal posterior distribution. And so from a Bayesian perspective, there is no unit root problem in that sense. You would get a normal posterior distribution. You would take the posterior mean and subtract twice the posterior standard deviation, and that will give you the Bayesian probability interval. However, if the true value of the autoregressive parameter is in fact equal to 1, it's not the case that conditional on the parameter, the maximum likelihood estimator or the least squares estimator is normally distributed, and you don't get you can't construct a confidence interval by taking the least squares estimate plus or minus 2 standard errors. That doesn't have the right coverage if in fact the parameter is equal to 1 or if the parameter is close to 1. And so in that case, you're forced to choose between these different paradigms, and I think there sort of taking the frequentist perspective makes things very complicated, because you end up with confidence intervals that can look very awkward. I think in this case they're not necessarily a simple interval, but it can actually be disconnected sets. I think they can be empty in some cases, but it's a lot of work to get frequentist confidence intervals, even though it's extremely simple to get Bayesian probability intervals. And so there's a very nice paper by Simpson and Ullek in Econometrics 91, where they discuss this problem at great length, and they look at the behavior of the likelihood function and why these problems arise. But so in that case, you do have to take a stand on what you're trying to get at. And so personally, I find it very hard to see the case for looking at frequentist confidence intervals. And I think that there's certainly a number of people in the profession who agree with that. There's certainly a number of people in the profession who disagree with that. But I think the large majority is sort of somewhere in the middle, where they look at problems where it doesn't really matter, and where it doesn't. It's not a question you're really forced to answer. Now let me talk a little bit about the practical issues of doing Bayesian inference. And so traditionally, sort of up to the mid-80s, early 90s, so there was this general setup where you specify any prior distribution in a model, and then you can figure out what the posterior distribution is. In practice, you couldn't actually really do that. And so in practice, so that if you had this normal, suppose you have a normal model for the data, then you pretty much had to pick a normal prior distribution, because otherwise you couldn't do the calculations. And so there was sort of always this bit of a disconnect between what was being preached about the generality of this and what you could actually do in practice. Well, you can choose any prior you want, as long as it's a normal prior, because otherwise you can't really implement this. But this numerical literature sort of developed a very powerful set of methods for obtaining draws from the posterior distribution given the data. And so the idea would be to just generate, to sample from this posterior distribution and then approximate the posterior mean by just taking the average of these draws. And so there's a couple of key ideas that make that work in extremely complicated models. So I just want to briefly mention these three ideas and sort of give some sense why this can be really powerful. And so the general idea is to construct a sequence, construct a chain of values such that for large, that after doing this for a while, theta k can be viewed as a draw from the posterior distribution of theta given the data. And so the way you get there is to set up an algorithm that, given a current value of the parameter theta k and given the data, gives you a distribution to draw from. You draw from the distribution, you get a new value theta k, and if the original theta k, you get a new theta k plus 1. If the original theta k came from the posterior distribution, then the next one will also come from the posterior distribution. This sort of seems a little circular, because now you need a draw from the posterior distribution to start this, but sort of what turns out to be this is in most cases, irrespective of what the starting value is, if you just do this for a while, you can interpret theta k as a draw from the posterior distribution of theta given the data. And so the way you implement this is you just pick pretty much an arbitrary theta naught. You then run this chain. So in the terminology of this literature, you run this Markov chain Monte Carlo for a while. You get a million values, theta 1, theta 2, up to theta a million. They're not independent, but they're all coming from the marginal distribution. And so, because as long as they're not completely dependent, as long as the dependence is somewhat limited, you can estimate the posterior mean by just averaging the last k minus k naught values. So you let this burn in for a while. You let it to take out the effect of the initial starting value. You let this run for a while, and then it's throwing away the first k naught minus 1 draws, and then the last capital K minus k naught you average to get the posterior mean. You calculate the second moment from that to get the variance. And so that is all sort of that's sort of the general idea. And then what's happened in this literature, that there have been a couple of very specific insights that can make this work very well in practice in models where other methods weren't working particularly well. Because obviously at this point it's not clear why it would be so easy to come up with, sort of the key thing here is obviously to come up with this distribution f of theta given theta k and the data. And so there's a couple of insights. And so one insight is the Gibbs sampler idea, to partition the vector of parameters theta into two or more parts, and instead of sampling theta k directly from some conditional distribution of theta indexed by theta k in the data, it may be easier to sample one given the other and the other given one. So for example, if you're trying to sample from a joint normal distribution, from a bivariate normal distribution, maybe it's difficult to sample from a bivariate normal distribution, but it would be very easy to sample from a univariate normal distribution. You do one first, then the other, and then keep iterating between these two. Now that's sort of a very simple example, and there it's actually not very hard to sample from a joint normal, but I'll give some examples, and these empirical examples later make it extremely useful to partition this parameter space into parts where it's very easy to sample from one given the other, and the other given the first. And so the second one, and that's sort of, you can also view that as sort of part of the Gibbs sampler, is an idea called data augmentation. And so here, let me just illustrate that with an example. Suppose we're interested in a sensor regression model, a Tobin model. There's some latent variable that follows a linear model, y star is x beta plus epsilon. What we observe is the maximum of 0 and y star. I suppose epsilon has a standard normal distribution. We could free up the variance as well, but that's not really an issue here. So if we actually observed y star, this would be very easy. We would just have a linear model. We have a linear model. If we have a normal prior distribution for beta, there would actually be an analytic solution for the posterior distribution. But we don't observe y star. All we observe is the maximum of 0 and y star. And now there's no analytic solution for the posterior distribution, and if beta is sort of reasonably high dimension, trying to integrate out the likelihood function to get the posterior distribution would be extremely difficult and messy. So what is the way to deal with that? The insight is that it's very useful to view both the latent variables, the y stars, and the betas as potentially unknown random variables. Obviously, we observe some of the y stars, but the ones that we don't observe are going to be viewed here as random variables. And so then the sort of data augmentation combined with the Gibbs sampler consists of two parts. First, given a current value of the parameters beta, we draw the missing, we impute the missing y stars, not by that conditional mean. We draw from the conditional distribution of y star given the data and given beta. So if we actually observe y star, that's a degenerate distribution, but for the ones where what we observe is y is equal to 0, y star comes from a truncated normal distribution. That's very easy to draw from, and that's very fast. We do that for all the missing observations given this initial parameter beta k. Then in the second step, given all the partly observed and partly simulated y star, we draw from the conditional posterior distribution given the data and given the y stars. That again is just a normal posterior distribution, so it's very simple to draw from. And now we're going to iterate that, because obviously for imputing these y stars, we just use a single value of beta, so that isn't necessarily the right value of beta. We need to sample from different values of beta, and we do that by sequentially going back, so by going back and forth between simulating these missing y stars and drawing from the posterior distribution of beta given the y stars. You do that 1 million times. You take the last 900,000 values of beta. Those are viewed as random draws from the posterior distribution of beta. And in this case, there's no way of getting an analytic solution for the posterior distribution. Doing this by numerical integration, actually directly getting the form for the posterior distribution is pretty much impossible if you do this for beta with dimension greater than 5 or so. But getting draws from the posterior distribution is extremely easy. It's sort of, you set it up in a couple of, it's very easy to program, and then it's a matter of letting the computer run for a little bit, and you get all the draws you want. And so this idea is just extremely widely applicable. There's a lot of work. So some of Rossi's work in the discrete choice case does this for multinomial probit models, and I'll come back to that later. But almost all these latent variable models, the feature is that the analysis would be so much easier if we observed the latent variable. And these Bayesian computational methods exploit that by imputing these latent variables and then iterating between that imputation step and the analysis given the complete data. The last sort of these insights, in some sense, this is the most general one, and sort of allows you to deal with all the cases that you can't really take care of directly with data augmentation. Again, we're interested in drawing from a particular posterior distribution, and the idea is that it may be easy to evaluate the likelihood function, but it may be difficult to draw from that. And now the idea is to draw from some relatively arbitrary distribution and accept or reject the draws with some probability that depends on the ratio between the posterior and the candidate value and this distribution we're drawing from Q of theta. So you calculate this probability rho, and we accept the new draw with probability rho and reject it with probability 1 minus rho. Ideally, you would draw directly from the posterior distribution, but the whole point is that that's typically very difficult. But using any widely dispersed distribution will work here. And so the way you use this in practice is to use a normal distribution or with a relatively high variance, and use that to generate the draws, and then accept or reject them with probability coming from this ratio. Okay, so now let me spend the rest of the time on some of these examples. And so there's a whole series of paper by Rossi, McCulloch, and Allenby, and various co-authors. This is a fairly early one. And so, in fact, sort of the model is more limited than what they have used in subsequent work, but I like the application here. So they're interested in sort of optimal design of coupon policies. The idea is sort of supermarkets could give blanket coupons to everybody, but they may do better. It may be profitable to make the value of the coupon differ by household or by individual. And so you may give individuals or households that are more price sensitive coupons of different values than households were not. Or if you're doing so the application here is to demand for cans of tuna. So if there's a particular household that only buys chicken of the sea, you might have to give them a big coupon before they're willing to buy. I don't actually know any of the other brands, so I'd have to look that up. But Starkist, yeah. But it's clear that sort of in principle you might want to tailor the value of the coupon to the individual you're giving the coupon to. And you see, a very simple way would be if you actually had individual information about these households, sort of their income or their demographics. But you could imagine that with the scanner data, you may actually know for each household what they bought before, and so you may try to tailor the value of the coupon to their whole purchase history. And so in order to do that, you clearly for some households, you're going to have a lot of data. You're going to be able to estimate very precisely how sensitive they are to price changes. For other households, you know pretty much nothing, and there's nothing you can say about the optimal value of the coupon for those households. And so you're not going to be. You shouldn't try. Well, there's two things. One, you need to allow for a lot of heterogeneity in individual preferences to make this work. Because if everybody is equally price sensitive, then a blanket coupon is going to be the right thing to do, no matter what the data, what the results are of a model with constant elasticities. But given that for some households you're not going to be able to estimate things very precisely, you don't want to just estimate these models all separately. And so what Rossi, McCulloch, and Allenby do is use a hierarchical random coefficients model where they allow each household to have individual preferences, individual household-specific preferences for the different characteristics of these goods. And so I guess this is pretty much a standard setup in demand analysis in I/O these days. You have a utility for household I, product J, and purchase time T. Depends on the characteristics of the product at that particular time. So actually the X should be indexed by J. This should be a J. With household-specific coefficients beta. And then there's a epsilon ij t there that, added on that is independent across households, products, and purchase times. So the choice-specific characteristic here would be in this case, would be price, as well as some marketing variables, whether this particular brand is featured or not. And so here, in this analysis, all the choice characteristics are assumed to be exogenous. I think that's sort of always controversial in the I/O literature, but I'm not going to sort of address that here really. And so sort of partly to take account of the fact that for some households they have very few purchases, they have very limited information. You couldn't possibly estimate all these beta parameters separately. So the way they model this is by modeling the household-specific taste parameters beta as coming from a normal distribution centered at a mean that depends on permanent individual characteristics, plus some normal error term with some variance-covariance matrix for these unobserved components. Now, so in principle, this is really just a random effect setup, and so you could try to estimate the common parameters, the gamma here, the sort of factor loadings for these individual characteristics, the covariance matrix for the unobserved components. You could just try to estimate them using maximum likelihood. But partly what Rossi, McCulloch, and Allenby want to use this for is have this feed into this optimal coupon policy. And so they really need, for that in principle, they need the household-specific betas. And so setting this using a Bayesian perspective here will, in addition to giving you posterior distribution estimates for the common parameters, will give you estimates for the posterior distributions for the betas. And even though the model itself here may be normal, the marginal distributions of these betas aren't necessarily, well, in general, are not going to be normal. They come from mixtures of normals and sort of in a complicated way. And so, we wouldn't have a distribution theory for the sampling distributions for these beta heads. And so it's conceptually much cleaner to just look at the posterior distribution there and use that to figure out what the optimal coupon policy is. And so just to, and this is obviously not necessarily very helpful for implementing this for this particular case or for any other case, but just to give you a flavor of what implementing this would look like, you would sort of use a combination of these Gibbs and data augmentation steps. We want to draw from the posterior distribution of the betas, the gammas, and the sigmas, and the sigma j squares, which are the variances of the idiosyncratic utilities for the different choices. The way to do that is separate things in first augment the parameter vector with the latent utilities, and then separate it into a couple of different subsets of the parameters. And so the first one step is to draw the household parameters given imputed utilities and given values for the common parameters. That's going to be very straightforward because now you would have a standard normal linear model for the utilities given with the betas as these parameters and with a normal prior distribution at that point. And you can do that for each household. You can draw the sigma j squared sequentially because that's just a normal linear model with known mean and unknown variance. You can draw from the posterior distribution of the common parameters gamma and sigma given the betas, because that's going to be, again, a normal linear model. And the last step is just drawing the unobserved utilities given all the parameters and given the data. And doing this sort of one household, one choice at a time, conditioning all the utilities for all the other choices. This is going to be involved repeatedly drawing from a truncated normal distribution. So the key thing is that this, in principle, this huge posterior distribution with sort of, if we have n observations, we have n of these parameters, beta I, as well as all as well as the common parameters, can be broken up into a number of steps that are all extremely simple and straightforward to do. Putting them all together gives you a conceptually very straightforward way of getting draws from the posterior distribution of the household parameters given and sort of given the data. And so, just to illustrate this, I have some figures from this Rossi, McCulloch, and LMB paper. So here, for 10 of the households, sort of labeled there somewhere at the bottom of the figures at the top, for each of these households, they look at the posterior distribution for the price coefficient, taking into account different information sets. So the idea is that if the supermarket could only use demographics for choosing, so if the supermarket had no information about the households, all they could do is choose the same coupon value for each individual, for each household. But if they had more information, they might be able to tailor these coupon values more specifically to the households. And the different figures here show how much information the supermarket would be able to infer about the price coefficients for these particular households given different information sets. So at the bottom right, you see that if all they knew was demographic